Hello, welcome back from break. For the next part of class, we're going to be looking at a series of PowerPoints. You'll need your periodic table out. The periodic table looks something like this. I've marked mine up a bit, but please find this. You'll also need some markers, colored pencils, something to do some shading. So we're going to be talking about the periodic table today, and the periodic table was founded by Dmitri Mendeleev, and when he founded the periodic table, people knew about the elements of the periodic table, and the elements are each of the items that are found in these boxes, okay? But they had no system of organization. They didn't know how to organize them. So Mendeleev found that certain groups of elements had properties that reoccurred, that came about over and over again, and that they formed a pattern. And so what Mendeleev did was he took the elements they knew of and aligned the elements in vertical rows by property. So elements that had similar properties are in the same vertical row. And to this day, we still use this general idea of elements in the same column have similar properties. The other thing he did was he ordered them by mass. So if you look closely at the periodic table, you see that underneath each element symbol, there is a small number. So for He, which is helium, the number says 4.0026. Okay? That's called the mass number. So if you look at these as we go through the periodic table, they start at the upper right-hand corner. You start with 1, 2, and you go to the next row, and they get bigger. As you go across here, and then down the next row, they continue to get bigger. So what they did was they put them in order by mass number, and that's the mass of the element, how much it weighed, and then they grouped them by properties. So first thing we're going to look at is metals. And you find metals on the left-hand side of the periodic table, which is over in this area here, and they actually extend into this area. And the things about metals are they conduct electricity and heat well. They can be formed into flat sheets or into wires. They're shiny, and they lose electrons when they go through chemical changes. The next are nonmetals. And by the way, this PowerPoint is on Canvas, so you can link to that if you prefer to go a little slower. The nonmetals are the elements that are over in this area. So I've shaded them in red. So right now, let's actually have you do that. Let's have you mark these ones that I've circled in red. Go ahead and mark those all with the same color. And with that same color, you can go ahead and label them nonmetals. After you do that, let's go back and do metals. So the blue on my sheet are metals. So you can look and see that I outlined this section over here in blue, but I did not include this hydrogen at the top. Okay, this hydrogen is different. I actually put that in red because that is a nonmetal. But these columns are blue, and then all of these over here are also blue. So go ahead and shade all of those blue, including the ones down here at the bottom. These are all metals too. So we have our metals over here and down here, and our nonmetals over here. And the thing about nonmetals is they don't have as consistent properties as the metals. Most of them are poor conductors. They do not they're not good for using with electricity because they don't conduct the electricity. Let's see what else. They gain electrons through chemical reactions. So during chemical changes, they gain electrons. You'll notice that we have a dividing line here. So you'll want to go ahead and draw this on your periodic table, this dividing line. That dividing line is where the properties of the metals start to overlap a little with the nonmetals. So we're going to talk about this green shaded area next called the metalloids. If you haven't already, you'll want to shade the area labeled metalloids the same color and also label what it is. So these lie along the zigzag line of the periodic table, and they're sometimes called semiconductors. These are ones that you'll find in your electrical appliances, your iPhones, your iPods, things that need to be able to turn on and off quickly. You can manipulate them to conduct electricity or to not, and so you find them a lot in electronics. So I'm going to have you take a second here and try to classify each of these as a metal, a nonmetal, or a metalloid. Go ahead and pause the video and do such. Okay, so you probably figured out that sulfur is a nonmetal. Sulfur's abbreviation is S. That potassium is a metal. Potassium's abbreviation is K. It's over here. And silicon is a metalloid. It's Si. And krypton is a nonmetal. It's a Kr. We have a group of metals that are called transition metals, and because of where they're on the periodic table, their properties are not super predictable. So you'll see that I label transition metals here, and this whole area, all of these that make this little block here, are transition metals, as are these ones on the bottom. So please mark your transition metals on your periodic table. The next two sections, lanthanides and actinides, are on the bottom. We're not really going to be too worried about them. They're already labeled on your periodic table, but just so you know what they are, the numbers start with 57 and 89. So where these stars are here is where these lines would insert. However, most of those lanthanides and actinides are not actually found in nature, and since they're not found in nature, they do not have very consistent properties, and it would make the periodic table very bulky. So we don't generally include those in our periodic table. I'm sorry, we include them in the periodic table, but not in the main body of it, so we won't be talking about them much. So we have families and periods, and you'll notice up here on my periodic table, I labeled families and groups, so please make sure you do the same on yours. Families and groups are the different columns that we have on the periodic table. And I want you to put numbers on yours as well, starting over here, 1, 2, 3, 4, 5, 6, 7, 8. And those are the families of the periodic table. Along the side, we have something called periods of the periodic table. So here, hydrogen and helium are in period 1. Period 2 is lithium, beryllium, etc. 3, 4, 5, 6, 7. These help us locate items on the periodic table. So take a moment now and try to find each of these elements on your periodic table and label them by period and family. So if you stopped the video, you probably found that calcium is in family 2, period 4. Calcium is Ca. Cesium is in family 1, group 6. Family 1, period 6. Argon is over here, so that is in family 8, group 3. Chlorine is right here. That is in family 7, group 3. Chlorine is right here, and that is family 7, group 3. Oh, I probably said that already. Nitrogen is right here. Nitrogen is family 5, group 2. And within the periodic table, we have some special families. So the main ones we're going to talk about are the noble gases, the alkali metals, alkaline earth metals, and halogens. So right now I'm going to guide you through marking up your periodic table to show those. Okay, so the first special group we have is group 8. Okay, this group right here, these are called our noble gases. So you see I labeled that and colored them a certain color. An example is helium. These elements do not like to combine with other elements, and they are stable on their own. So please mark your periodic table there. The next special group of elements are the alkali metals. The alkali metals are the group 1 that starts with hydrogen, although we don't include hydrogen because hydrogen is not a metal. So it starts with lithium and goes down to francium. These are alkali metals, so I labeled alkali metals on my periodic table and shaded that column the same. So these are very, very reactive metals. Sodium, for example, explodes in water. These are often stored in oils and things so that they don't react with the air as well. The next group is the alkaline metals, alkaline earth metals. This is the group 2 of the periodic table. So I shaded mine in blue. I labeled it down here. Please be sure to do the same. These are fairly reactive. They're not quite as reactive as the alkali metals. And an example is magnesium. We'll see a video in just a few minutes about that. The next family is the halogens. This is group 7, okay, right down here. You'll see I labeled it halogens. And these ones are very reactive nonmetals. They don't often appear in nature by themselves. They're always combined with something else. So now take a few minutes and see if you can decide which special group each of those belongs to. So if you took that break and you did that, you probably found that bromine, Br, belongs to the halogens. Argon, Ar, belongs to the noble gases. Barium, Ba, belongs to the alkaline earth metals. And sodium, which is Na, kind of hard to find, belongs to the alkali metals. Just going to pull up one more PowerPoint here, so just be patient with me. So next today we're going to be looking at physical versus chemical properties and changes. So this PowerPoint again is on your Canvas if you'd like to pull that up. So when we talk about properties of a substance, we're talking about things that we can observe about it from our 5 senses. And these distinguish one thing from another. If I'm looking at the ping pong ball, you can see that it's orange, right? The ping pong ball also is light. It's made of plastic. These are some examples of physical properties. So a physical property is a property that a substance displays without changing its composition. So we're going to look at water as an example. So water is made of hydrogen and oxygen. I'm going to draw a quick picture of water here for you. This is a picture of water. It is H2O, okay, meaning it has 2 hydrogen and 1 oxygen connected. If you have water in a liquid state, it's like the water you drink. Water can also exist as a gas, like the steam that comes off of a pot of boiling water. It can also exist as ice, right? Ice in your refrigerator. So if we look at water, let's just think of some physical properties of water. And you might come up with that it's wet, that it's clear. You might come up with the fact that it's a liquid. These are all physical properties. You also could talk about what its weight is, what its mass is, those types of things. Here is a list of some common physical properties of matter. Please take a look. You'll notice that density is on here. We talked about density last week. Phase change refers to that changing from a solid to a liquid and a liquid to a gas. That does happen. When a substance changes from a solid to a liquid and a liquid to a gas, it stays the same compound as it was. So these elements, hydrogen and oxygen that make it up, they stay the same. So this stays the same when it's a physical property. But a chemical property is different. A chemical property determines how one substance can change into something else. So with our water example, it's possible to make water break apart into two different pieces, right? Where my hydrogen are separate and my oxygen. It no longer has this chemical formula. It would instead, you'd have two H's and one O. It would no longer be H2O as one. So think about gasoline, for example. We could burn gasoline and break it up, and then it becomes carbon dioxide and water, which we have come out of our cars. Here are some common chemical properties. I want you to think about if you can find an object around you, pick up that object and see if you can think about any physical properties that that object has. So here's my golf ball. It's plastic, it's hard, it's white. I could find the density of it, the mass of it, the volume of it. It has a black streak on it. It's bumpy. Okay. I can't offhand think of a huge number of chemical properties here, but I would guess that at some point this becomes flammable, right? Where I can make it turn into a flame. Let's think about a cigarette lighter. Cigarette lighter, you could definitely say that that has chemical properties, right? Because it can become flammable. What happens there is that you have a chemical change going on. You have the liquid in the lighter changing to a flame. And so it's interacting with the air, and the air helps change it into a flame. Things that also would be chemical properties are some things corrosive. So you've probably seen parts of your car kind of corrode around the battery, right? You get a substance there. It's changing. It no longer has the same chemical composition. Another example is rust, right? If your car is exposed to water and air, then it might start to rust. The chemical composition of rust is different than just the chemical composition of the material your car is made of, the iron. So I'd like you to identify each of these as a physical or chemical property. The shiny appearance of gold, so that should be a physical property. The density of copper, that should be a physical property. The increase in temperature when sodium hydroxide reacts with water. Since there's a reaction taking place here and a temperature change, then this would be a chemical property. Okay, let's look at what physical changes are now. So this is when matter changes its appearance but not composition. So this is what we were talking about before when we were talking about water changing from a solid to a liquid to a gas. That is a phase change. Another way we can physically change something without changing the composition of it is by cutting it or tearing it, right? So if I have a piece of paper and I tear it, I did not change what the paper's made of, but I changed its appearance. If I break a glass, the same thing happens. If I melt a cube of ice, all that happens is that the water changes form from a solid to a liquid. Can you think of any more physical changes? The next is a chemical change. So when a chemical change occurs, matter changes its composition. So when I was telling you about the water and the hydrogen and oxygen here, remember that if it stays with this form of water, if it keeps looking like this, it's a physical change. But if the arrangement of the atoms, of the elements, changes into a different form, then you have a chemical change taking place. So chemical changes often include color changes or heat changes. Think about a car rusting, right? It changes from its original color to the color of rust. Another example is copper turning green. Did you know the Statue of Liberty was once copper colored, and because of its exposure to air, it's turned green? This is an example of a chemical change because as the Statue of Liberty was exposed to air, the copper has changed color. So it's no longer the same copper material, it's been oxidized by the air. So I'd like you right now to take a few minutes and tell if each is a chemical or a physical change. Please pause and do that. Okay. The evaporation of rubbing alcohol when the bottle is left open, that is an example of a physical change. The rubbing alcohol is going from a liquid to a gas. The next one, the production of a flame when the liquid butane vapor encounters a spark when it's in a lighter and is lit. So that's what we're talking about in the lighter, your cigarette lighter. That is a chemical change. It's encountering a spark, and then it creates a flame. And then next is the melting of an ice cube. That's just a physical change. It's still water, right? The ice cube melts, it still has the same composition. And lastly, I'll play you this video, but this one should be a chemical change. So just a second, I'll show the video. Okay, they lit magnesium. They made magnesium and water combine, and this is the reaction you get. You can see there's a lot of flames involved, so there is color and composition changed here. Okay, I have one more PowerPoint for you. If you're really tired right now, you may save this one for tomorrow. It is up to you. The last PowerPoint is on mixtures versus elements and compounds. Okay, so we're going to start by talking about matter. And matter is anything that occupies space and has mass. This includes things such as air that we don't see. And matter appears smooth, but actually it's not. If you feel the table, it feels smooth, but it's actually made up of atoms and molecules that are actually quite rigid. So I'm going to draw you a little picture here. I'm going to put a bunch of circles to represent different atoms. And as I show you this, you can see that along the top, it's actually bumpy, right? It doesn't form a smooth surface, but our atoms and molecules are so small that we can't feel that small rigidness of them. So what atoms are is they're the smallest identifiable unit of an element. So when we had our periodic table, each of these individual ones are an element. So each block here represents one element of the periodic table. And molecules, what they are, is they're atoms that are bonded together. We can have elements classified as a solid, a liquid, or a gas. Solids are atoms that are packed really close together. So that's what I drew you a picture of earlier. Okay, that's an example of a solid. That's why solids hold their shape. And despite this, the atoms are still moving. So in this picture, we have these atoms still vibrating, even though it appears to us as though they're staying still. Solids cannot be compressed. You can't squeeze it together to be more condensed, and they have a definite shape and volume. Liquids are different because the atoms in liquids have more room to move around. So I'm drawing right now an example of where atoms might be in a liquid. So this is my example of a liquid right here. Okay. There's some room for them to move around. Liquids cannot be compressed. Think about my water bottle here. Okay. I can't compress this liquid. I can't squeeze it any more together. And it has a fixed volume, but that volume can take the shape of the container. So if I turn my container, it's going to move with it. So some examples of liquids at room temperature are water, gasoline, and mercury. Next are gases. So gases are when atoms and molecules are separated by greater distances. So I will quickly draw you a picture of that. In this example, the molecules are moving around and they bump into each other a lot less frequently than they did in the solid or the liquid. Because of this, gases can be compressed. So you may have seen a helium tank where they compressed helium gas from the air from somewhere else into a condensed place. And the gas has to take the shape of the container. It doesn't hold a shape on its own. And they also do not have definite volumes. So take a minute and identify each as a solid, a liquid, or a gas at room temperature. So you probably said that a table at room temperature is a solid. Very good. Helium is a gas. Baking soda is a solid. Vinegar is a liquid. And gold is a solid. Okay, I'd also like you to identify each of these as an element or a compound. So an element is when you have one element by itself, such as one that's found on the periodic table. If it's not found on the periodic table, if you can't find the name of it on the periodic table, then it's probably a compound. So take a few minutes and see if each of these is an element or a compound. Okay, we'll move on. An iron rod is an element. Water is a compound. Water is made of oxygen and hydrogen, so it's made of two elements from the periodic table. A lead weight is made of lead, so that's an element. Carbon dioxide has carbon and oxygen in it, so that is a compound. And acetone is essentially nail polish remover, and that is a compound as well. You could not find that on the periodic table. Okay, so here's where we're getting to the more interesting stuff. So we can identify things as pure substances, if they're elements or compounds, or mixtures. And there are two different types of mixtures we'll be talking about, heterogeneous and homogeneous. So pure substances are made of only one type of atom. These are ones, like we said, that are elements that are found on the periodic table. So if a substance is made of sodium, it would have only sodium in it. It would not have anything else. And sodium atom is the smallest bit that can exist without it losing its properties. A compound is when you have two or more substances that are together in fixed proportions. So that's like the water that we talked about earlier. So the water molecule is made of hydrogen and oxygen. It's made of 2 hydrogen to 1 oxygen. It stays that way. So a compound can be made of 2 elements or many more. So the mixtures is where we're going to spend most of our time. Most things are mixtures. If you think about soil, you have a mixture of sand and compost. You have a mixture of maybe some clay in there too. Air is a mixture of oxygen, hydrogen, nitrogen, carbon, many different things. Okay? Mixtures do not have set proportions of the substances that make them up. And there's 2 kinds of mixtures. There's the heterogeneous, and heterogeneous mixtures mean that they're not the same throughout. So think of vinegar and oil salad dressing. Okay. If you think of vinegar and oil salad dressing, you have the vinegar at the bottom and the oil at the top. They're not evenly dispersed. They're separated out into 2. However, if you have a container, let's say something like salt water, and the salt particles are evenly dispersed throughout the water, like this, so these circles represent the salt, then that is called homogeneous. So you want to get these 2 words down, heterogeneous and homogeneous. Okay, so we're going to think about each of these, if they're the same throughout or different. Take a few minutes, think about it, write down your guesses. So Italian salad dressing. This would generally be heterogeneous. You have the separation of the oil and the water and spices. Chicken noodle soup, generally heterogeneous because the noodles are going to be floating on the top where the broth is more in the bottom and the vegetables are somewhere in between. It's not evenly distributed throughout. Distilled water is just water. The various elements of water would be evenly dispersed throughout. River water, you could argue either way. Generally, I would think of river water as being heterogeneous because you might have more muddy water at the bottom where the water might be clearer towards the top or towards the middle. And coffee. Unless you drink coffee that has a lot of grounds in it, or if you add cream or sugar and don't stir it, you probably have coffee that is homogeneous. But if you don't stir the cream in, it's just sitting on top, that makes it heterogeneous because you have a layer of cream that's not evenly distributed throughout the coffee. If you have grounds in your coffee, they're going to probably sink to the bottom. That would also make it heterogeneous. Hi there. I'm going to pause this for a second. Hi there. Yeah.